Welcome to this fourth episode in our series on calculations that you might be asked to make in molecular biology. And today we're going to be thinking about multi-component solutions. In previous episodes we've thought a bit about units and powers in general, we've thought about some of the sorts of mole calculations you might be asked to do, and about calculations that involve volume changes or dilutions. And in this episode, and in the next episode afterwards, we're going to move on and think about calculations that involve solutions with multiple components. Now that might sound alarming, but what I hope we're going to see is that these are simply slightly larger versions of the calculations that we've done already. So let's take an example to begin with. Describe how you would prepare 350 millilitres of a solution containing 10% glucose when you've got a stock solution of 40%, 25 millimolar tris base made from solid, and you're told that the relative molecular mass is 121.1, 10 millimolar EDTA from a 0.5 molar stock, and 2 micrograms per mil of bovine serum albumin from a 10 mg per mil stock solution. It looks quite complicated compared with the sorts of calculations that we considered in episode 3, but actually, if you break it down, there are simply 4 different calculations to do within this. So what we're being asked to do is to make up a 350 milliliter solution containing 10% glucose, 25 millimolar tris, 10 millimolar EDTA, and 2 micrograms per mil BSA from a variety of stocks, in one case from solid, and then finally to dilute that to 350 millilitres. So we can break down the calculation into each of those different components, and then only at the very end do we need to think about combining that and what difference it makes to bring them together for a total volume of 350 mils. So let's begin by thinking about the first of those components, the glucose. Prepare 350 millilitres of a solution containing 10% glucose from a 40% stock. The first thing that I would do, as always in these calculations, is probably not to write down initial volume times initial concentration, is final volume times final concentration, but I would literally write down VI times CI equals VF times CF. And as we said before, sometimes the initial is called the stock instead, so VS times CS. So I'd write that down to begin with, and as always in these sorts of calculations, we've been presented with 3 bits of information and we need to work out the 4. So the first thing to do is to put in the information that we know. So we've got 40% is our stock solution, 35 millilitres is our final volume, and 10% is our final concentration that we want for the glucose. So on this occasion our unknown is the initial volume, and you'll note there that I've included in that line of the calculation are units, just to make sure that I'm not going to end up by a factor of 100 or a factor of 1,000 out. As it happens on this occasion, the units match for the percent before and afterwards, so I know that my answer, the unknown volume, is going to be in millilitres, the same as we've got on the right hand side. So I can see then that my unknown in millilitres is 40% times 250 mils times 10%. I can work through the calculation, 350 times 10 divided by 40, and that gives me an answer of 87.5 millilitres. So the volume I need from my glucose stock solution is 87.5 millilitres. I can put that to one side. I can move on to the calculation for the second component, and that's the tris base. Now on this occasion, the tris was being made from a solid. So the calculation is slightly different. Again, we've seen calculations of this sort in previous episodes. So I would begin by saying that my final solution needs to contain 25 millimolar. What does 25 millimolar mean? 25 millimolar means 25 millimoles per litre. Now I don't need a litre, I need 350 millilitres. So 25 millimolar also means 25 micromoles per mil. Now I know that every 1 milliliter has 25 micromoles in it, and I want 350 of those altogether. So we need 350 times 25 micromoles that we're going to have, and that's 8,750 micromoles. Now we obviously don't want to leave it in that large number, so that is the same as 8.75 millimoles. Now that's not actually the end of that particular section of the calculation. We need to now work out what that's going to be in terms of mass. So if we need 8.75 millimoles, we need to know straight away that 1 mole is 121.1 grams. We get that from the relative molecular mass. And so therefore it follows that 1 millimole would be 121.1 milligrams. Now we actually want 8.75 millimoles, so we're going to need 8.75 times 121.1, which is 1059.6 milligrams, or 1.06 grams would be sufficient accuracy for that calculation. Okay, so we know our first component, the glucose. We know how much we need for the second component, tris base. We can then move on independently to think about our third component, which is the EDTA. So again, I would start by writing down VI times CI equals VF times CF. Which are the 3 bits of information that we know? What do we want to add to that? We know that our final concentration is going to be 10 millimolar. Our final volume, as is standard in the question overall, 350 millilitres. And my stock is 0.5 molar. Now, as we can see here straight away, the stock unit and the final unit are out. They're different by a factor of 1,000. So I want to begin by making sure they're the same on both sides, so I can convert 0.5 molar and state that as 500 millimolar instead. And now I know, because these are the same concentration units on both sides, my unknown volume unit is now going to be millilitres, because it matches the volume on the right hand, the volume on the right hand side. So my unknown in millilitres is going to be 350 times 10 divided by 500, which is 7 millilitres. And then the last thing we need to work out is our fourth component, the bovine serum albumin, BSA. Again, I write down VI times CI equals VF times CF. I put in the components that I know. That's our stock concentration for the BSA, which is 10 mg per mil. Our final volume, which in all cases in this question is 350 mils. And my final concentration is going to be 2 micrograms per mil. So again, the units of concentration on the two sides here are different from each other. I want to make sure that they match. And so that was a slightly tricky number to deal with, because we had such a big disparity between 10 mgs and 2 micrograms. So we were going to have to make either one number very big or one number very small in order to match the units. And I've elected to make the units on the left-hand side, the number on the left-hand side, be very large to fit with that. Because now I've got micrograms per mil on both sides, I know that my unknown is in millilitres, because it's the same as we've got here on the right-hand side. So my unknown number of millilitres is 350 times 2 divided by 10,000, and that's going to be an answer of 0.07 millilitres, or in other words 70 microlitres. So I've independently worked out how much glucose, how much tris base, how much EDTA, and now how much BSA, and I can put all that information together to make up my solution. I know that I want 87.5 millilitres of glucose, 7 mils of EDTA, and 70 microlitres of BSA. And into that I'm going to add 1.06 grams of tris base. Now the volume so far doesn't add up to 350 mils. And there is the temptation that I might say, well, let's work out how much additional volume we need, and I'll just simply add that in. But as you may remember from an earlier episode, that would be actually to introduce a mistake, because the tris base itself has volume. It's a solid, but it's going to add to the volume overall. So in order to actually end up at 350 mils at the exact concentrations that we want, we're going to need initially to have a slightly lower volume. Now at the moment our volume's a long way short of what we want, so I could add a fairly sizable amount, for example 200 millilitres of water to that, and still be considerably short of the final volume of 350. And that adding that water just makes sure that we're going to get the tris base properly dissolved into the solution. Now, we haven't actually in this calculation mentioned anything about making sure it's correctly pH'd, and we're not going to get into that in this particular video, so let's leave that to one side for the moment. If we're just going to now make up the volume to 350 mils, then all we need to do is add the solids to our 95 mils plus our 200 mils of water, and then eventually, once the solid has been dissolved, as I say, pH is necessary, although we're not discussing that in the current video, then we make up the final volume accurately to 350 mils. And then I can be confident I've got the right volume at the right concentrations for all my various components. So that's a multi-component solution, simply lots of different versions of a simple volume calculation being put together. And in the companion video on this particular topic, we're going to think about a different style of multi-component solutions.